Hello, everyone. My name is Wang. Currently, I am a doctoral student at the School of Computer Science and Technology, North University of China. As you can see, my paper, the source image is the best attention for infrared and visible image fusion, has been accepted by ICCV 2025. So now let me introduce my job to you all. Before introducing this article, we must first introduce another article published at ICCV 2017, namely GradCM, Gradient Weighted Class Activation Mapping. All right, we don't need to understand it in great detail. We just need to know that GradCM is a technique for visualizing and analyzing the decision-making process of the model. Let's take a classic image classification model, ResNet 50, as an example. If we input an image containing a dog and a cat into ResNet 50, at this time, the classification result of ResNet 50 for this image may be cat or dog. Then, we use GradCM to analyze the situation where the classification result is dogs. At this time, the result of the visualization analysis shows that the area where the dog is located is marked in red, and the area where the cat is located is displayed in blue. Similarly, when the classification result is a cat, the area where the cat is located is marked in red, and the area where the dog is located is displayed in blue. In fact, this transition from red to blue is a color mapping algorithm known as JET. In the visualization analysis results of GradCM, you can understand it as the closer the area is to red, the greater the role it plays in the decision-making result. Conversely, the blue area contributes little or no to the classification result. Now, let's further observe more visual analysis cases of ResNet 50 decision-making. The images in the cases are all taken from the ImageNet val set. For the sake of convenience and expression, we refer to the visualization result obtained after analyzing the ResNet 50 decision-making layer using GradCM as the GradCM image. At this point, you can see that the area where the dog is located in the GradCM image is marked in red, while the rest is represented as blue. Just now, we mentioned that in the GradCM image, the closer the area is to red, the greater the effect on the decision result, while the closer the area is to blue, the less or no contribution is made to the classification result. Now we can understand its meaning from another perspective. From another perspective, we can understand the red areas as the regions that the model is more concerned about and interested in during the decision-making process. Here, we define the regions that these models are interested in as important regions, and similarly, the blue regions that the models are less interested in are defined by us as general areas. Now, let's officially move on to the topic of our work. First, we select two GradCM images from the previous slide, and then randomly choose an infrared image from MSRS, a popular infrared and visible image fusion dataset. Now, let's observe what similarities there are between infrared images and GradCM images. Well, if you still can't see it, we'll further display this infrared image in the form of JET. Can you see the similarities between the two now? Yes, you can easily observe that both GradCM images and infrared images are composed of important areas and common areas. That's amazing. What needs to be added is that in infrared images, important areas are manifested in places with higher energy, while general areas are in places with lower energy. Furthermore, we have just interpreted the GradCM image from another perspective as an attention map, in which the model pays different degrees of attention to different regions during the decision-making process. Then, can we also directly regard infrared images as a kind of attention map? That is, does the infrared image naturally possess an attention property based on heat distribution? Well, this is precisely the core idea of this work. To confirm our conjecture, we conducted a statistical-based verification based on the MSRS dataset. Specifically, we input infrared images into SIMM, a parameter-free attention module published on ICML 2021 and get attention maps. We then compute the cosine similarity and Pearson correlation coefficient between infrared images and attention maps, yielding the results of 0.983 plus or minus 0.003, p equals 0, and 0.982 plus or minus 0.005, p equals 0, respectively. The extremely high results and p-values are sufficient to prove that infrared images can be directly regarded as attention maps without any processing. We have confirmed the inherent attention properties of infrared images. Now, let's take a closer look and see if the attention pattern of infrared images has greater advantages compared with grad-CM images. Yes, the first advantage is that compared with ResNet 50, it requires a large amount of training to learn the attention pattern, while this attribute of infrared images exists naturally. The second advantage is that the attention pattern of ResNet 50 is not accurate, while the infrared image is a precise guidance for heat distribution. The specific explanation is ResNet 50 only focused on the eyes of the dog in the first grad-CM image, while the nose, ears, and claws were not noticed. In the second grad-CM image, ResNet 50 not only focused on the entire dog, but also paid excessive attention to the irrelevant grassland around the dog. However, infrared images are controlled the distribution of heat precisely and do not focus on irrelevant areas. All right, now we have discovered that infrared images not only inherently possess a property of attention, but this property is also more accurate and specific. So the next question is how to use this attribute in the process of infrared and visible image fusion to better complete the task. Before answering this question, let's first take a look at the general process of common infrared and visible image fusion, IVF. As shown in the following simplified diagram, IVF can roughly be divided into 4 stages: input, feature extraction, feature fusion, and output. Well, are there any problems with the process? Or are there any areas that can be improved? Yes, we can introduce a cross-modal feature interaction module before feature fusion to share the pressure during the feature fusion stage. Because it is very difficult to achieve a good fusion of the completely unrelated infrared features and visible features extracted in the previous stage through just a few convolutional layers. Introducing a cross-modal feature interaction module is actually to complete the interaction and fusion of some features in advance before the final fusion. This is equivalent to us doing a preview in advance before the teacher teaches new knowledge. Could there really be anyone who can understand what the teacher is saying without previewing? I still think it's better to sleep in class. So, how should a cross-modal feature interaction module be designed to fully utilize the attention properties of infrared images themselves? The specific approach is that we directly link infrared images with the attention mechanism. Whether it is the attention property of the infrared image itself or the attention mechanism, there are actually different attentions to different parts of the global information, and the two have the same connotation. Specifically, we propose the source infrared cross-attention, abbreviated as ISCA, by modifying Restormer, an article published in CVPR 2022, and the structure is shown in the figure. ISCA consists of 2 parts, namely the dual conv infrared cross-attention, IDCA, and the gated conv feed-forward network, GDFN. We only need to focus on IDCA now. In IDCA, we directly regard the infrared image as Q, while the intermediate features of the visible modal after feature extraction are regarded as K and V. Through this natural prior guidance of infrared images, we can activate more visible features at the corresponding positions of high heat regions in infrared images, thereby obtaining a representation that interacts with visible features based on the prior guidance of infrared image heat. However, the above-mentioned approach still has a serious drawback, That is, unlike tasks such as object detection that only need to focus on specific categories, image fusion needs to take into account every pixel. However, in the previous stage, we only considered the prior guiding role of the important regions in the infrared image, which is obviously incomplete. So how can this problem be solved? Here, we adopted a simple operation. That is, we directly applied negative transformation processing to the infrared image, and then regarded the negative image as another cue. In this way, the attention complementarity between the important areas and the general areas can be achieved. It seems that everything is ready, but is that really the case? No, we also overlooked another issue. That is, in ICCA, the channels of Q, K, and V should remain consistent. Otherwise, the calculation of attention cannot be carried out. The original infrared image has one channel, while the intermediate representation of the visible image is multi-channel. Therefore, it is necessary to perform the channel boosting operation on the infrared image first. Thus, we deployed a channel boosting and space mapping module, abbreviated as CBSM. It consists of convolutional layers, activation layers, and in squeeze-in excitation, southeast operation. In addition to the basic function of enhancing the channel of the source image, CBSM also has two important functions. The first one is to transform the initial space of the source image. Its significance is to narrow the gap between features at different stages, as this will seriously affect the effect of feature interaction. The second function is implemented by the SE operation, but we won't discuss it for now. I will introduce it in detail later. Here I must explain why the design of the CBSM module is so simple. You might think it lacks innovation, and indeed it is. Simple modules can be freely combined by anyone, can't they? But what I want to say is that we did not adopt such a simple module unintentionally, because our core motivation is to guide the feature interaction of different modalities with the most primitive infrared images. If complex modules are used, it is highly likely to destroy the initial patterns in the source images, thus contradicting our original intention. Now that we have taken all the problems into account and provided corresponding solutions, based on all the above analyses, we have designed the following model. Okay, I admit that my drawing skills are indeed very poor, but let's not talk about it for now. Let's first introduce its composition. It can be seen that it is divided into several stages, such as input, initial feature extraction, deep feature extraction, cross-modal feature interaction, feature fusion, and output. This is consistent with the general process of infrared and visible image fusion we introduced earlier, so it will not be elaborated further. But what I want to add here is why another feature extraction was carried out after the initial feature extraction. Well, you can see that in the initial feature extraction stage, we used the SERESNet block, which is a component based on convolution operations, while in the subsequent cross-modal feature interaction stage, the attention mechanism was used. To achieve a smooth transition between convolution and attention, we added a restorer block, i.e., a self-attention operation, before feature interaction, thereby transforming the feature space from the domain where convolution excels to that where attention excels, so as to better complete the cross-modal interaction process. So, does that mean all the designs are done by now? In fact, it's not completely over yet. In the feature interaction stage of the previous slide, we only used infrared images and their negative transformations for cross-modal feature guidance, and completely abandoned the role of visible images. Although visible images do not visually possess the distinct attention patterns that infrared images exhibit, but we think they're visually significant regions, e.g., edges, textures, and contrast, can still serve as effective priors. Therefore, we symmetrically extended our findings on infrared images to the visible modal and ultimately defined the model as shown in the figure. Well, it's particularly ugly too. One point that needs to be clarified for this final model is that, except for the different inputs, The operations of ISCA and VSCA are completely the same. You might have a question. Can this completely consistent structure reflect the differences between different modals? My answer to this is yes. That's completely fine because their inputs are completely different, which directly leads to them paying attention to different information during the interaction process. Specifically, ISCA emphasizes the heat distribution, contours, and structural priors of infrared images, while VSCA focuses on edges, textures, and high contrast guidance. Another question is whether using both the source image and the negative transformation simultaneously will introduce a certain amount of information redundancy. My answer to this question is also yes, but this problem can be completely avoided by the GDFN submodule in ISCA and VSCA. Because the GDFN module functions as a gating mechanism, it can control the information flowing through, thereby suppressing redundant information. However, it should be emphasized that the GDFN module was designed by Restormer, and we merely took advantage of this feature of it. Now let's address a question left over from before, namely, the role of the SE operation. You can see that, whether in CB Sim or in the feature extraction or feature fusion stage, we have all used the SE operation. You can also simply understand it as a gating mechanism, which plays a role in suppressing redundant information, just like the GDFN mentioned earlier. However, in the CB Sim module, the SE operation also has an additional function, that is, to suppress misleading information in the source image. Because our article adopts the approach of directly treating the source image as a query, but not all the information in the source image is positive. It may also have negative impacts. At this point, the SE can play a role in dynamically adjusting the query, thereby reducing the negative impact in the query. In addition, in order to minimize the negative effects in different queries as much as possible, we respectively used separate, non-shared CB Sim modules for infrared images and their negative transformations, as well as visible images and their negative transformations. By now, my introduction to my article is basically over. The experimental and ablation aspects have been elaborated in detail in the paper, so I won't go into more detail. But I need to add some places that did not appear in my paper. The first one is the robustness test of the model we proposed. From the above introduction, you can see that the model we proposed is mainly driven by infrared images. In real life, infrared images are easily disturbed by various factors, such as low resolution, occlusion, and thermal noise. For this purpose, we conducted robustness experiments on MSRS. The specific approach is as follows. For the low resolution part, we randomly downsample the infrared image by 3, 4, or 6 times, and then upsample it back to the original resolution. For the occlusion part, we randomly generate 1 to 3 black occlusions on the infrared image, which account for 10 to 40% of the image. For the thermal noise part, we added Poisson noise with a temperature coefficient of 0.12 and an amplitude of 8 to the infrared image. Finally, we randomly applied 1 to 3 of the above-mentioned mixed effects to the infrared images. We then reconducted the experiment using degraded infrared images and compared it with 2 competitive methods, CDD fuse and SWIN fuse, and the results are as follows. Although the performance of our proposed method is slightly better or comparable under various interferences, it is undeniable that the accuracy drop of our method when infrared images are subject to more interference is slightly higher than that of the 2 comparison methods. Moreover, our model also does not perform well in all situations. For instance, in the fusion effect of the following image pair, although our method retains the details in the red box well, it loses the trees in the green box. In contrast, LRRNet and Metafusion have completely preserved the trees. So, this gives us an opportunity to re-examine ourselves, that is, where our discoveries, core ideas, and models can still be improved. So our next established goal is to design more targeted modules or conduct a more comprehensive methodological analysis to make our method more perfect. In the end, what I need to add is that since the submission time of the ICCV is at the beginning of 2025, we failed to incorporate the latest methods of 2025 in the selection of comparison methods. However, some experimental experiences tell us that the effect of CDD fuse in the comparison method chosen in the article is indeed excellent. Its effect can still surpass many of the latest methods, even by today's standards. The introduction is complete here. To sum up, our main contribution is that we drew inspiration from GradCM images and reveal for the first time that infrared images themselves possess a natural attention property. Then, we adopted a feasible way to utilize this property in the fusion of infrared and visible images. This leads us to propose a new image fusion pipeline based on the source image itself. Finally, I would like to sincerely thank the reviewers and area chairs for this article. Thank you for your recognition and support of this work, and for the very meaningful and valuable suggestions you have put forward. This is all the content of this article. I hope it can be helpful to you. If you can attend the conference in Hawaii, you're welcome to come to our booth for communication. If you have any questions to consult, you can also contact me by email. Goodbye.